precision agriculture, and I'll hint in one or two spots that we can help there. Now, that was the vision, but if you look at what's happening in the press, there's a lot of things that don't go well, especially the self-driving car world. In fact, as a reminder, 5 years ago, in 2015, we were promised that in 2020, it would be the year of self-driving cars. So you were going to go to a car dealer and buy one of them. And of course, recently there has been a realization that this is a long road ahead towards achieving autonomy in not just in self-driving cars, but all kinds of intelligent machines. And to some extent, the talk will be about some things that we can do to get there. But I'm not going to be able to address all of them. Our research group that has all elements of autonomy. Okay, so I would like to first start the talk by talking a bit about 4 trends that I see. So if I look back, one major accomplishment over the past decade has been deep learning. And that has revolutionized, of course, the way that we perceive the world. And this is an area, of course, that is extremely competitive, hot, and trendy right now. But it has enabled a future where robots can go out in the physical world and perceive things and make sense of the physical world and understand geometry of the physical world or make segmentation. But if you look at the future, one challenge, and this is one of the reasons you see a lot of the failures in the self-driving cars world, is that machine learning is not very robust. Okay, these are some famous examples out there that if you can take an image and you pass it and you add some carefully crafted noise, you can get an image that's imperceptible. It's identical to the one that you had before, yet the deep learner, the classifier, would not only misclassify this as a gibbon, even though initially classified as a panda, it's also far more confident in the misclassification. And of course, this in the context of autonomous systems, which are safety critical, or even medical imaging, which is also safety critical, this would not make machine learning very trustworthy. Now, this was a carefully crafted adversarial noise, so you could have an adversarial view, but this is not just adversaries playing games, also nature can play games. For example, here, you can change the lighting in an image, and that can cause you to misclassify the direction of the road, and that could have catastrophic consequences as far as which way you're going. And there are other such attacks or misclassifications that can happen very easily, making them fragile and not very trustworthy. I'll get back to this later in my talk. The other trend that I see, and this comes from the area of robotics, and that is that in robotics, there's absolutely, it's absolutely the case that SLAM, the technology which does localization and mapping, has been a tremendous success. And it is now a commercial technology. It has gone out of the academic world and is now commercial technology. And SLAM is essentially a technology that, given sensor measurements, allows you to create geometric representations of the environment as well as localize yourself in the environment. And by geometric representation is you can make a very fine grid cell map, where what you get is information as to which cells are occupied and which cells are not occupied. Where should I, choose a path to have a collision-free path, and where I cannot. So it gives us a lot of information about the geometry of the environment, but it doesn't necessarily tell us a lot about the semantics of the environment. And that is one trend that I see going forward, and this is something else I'll talk a little bit about, which is that we are not just interested in the geometry of the environment that we operate in, we're also interested in the objects that we see. We're interested to know in an intersection whether the object we see is a pedestrian or a box. It really matters regarding our decision. Or we need to know whether, if we are in an unknown environment, exactly whether this, is a human or whether this is an animal. And the type of the object that we see, the semantics of the object, really matters for further intelligence in the longer term mission. So I'll talk a little bit more about this as well later. The other trend, and this goes to the planning and control community, is that the planning and control community has been working in a paradigm that is mostly like this, that we have some dynamics, which usually is known. We are given some representation of the map, which is typically also known, some geometric perhaps representation or some even graph representation. We're given some specifications, such as go from point A to point B and avoid obstacles. And then, you know, whether you use control theory or planning theory in robotics, whatever, you come up with trajectories that take you from point A to point B while avoiding obstacles. And, you know, when we send robots now in the wild, what happens is that, you know, this assumption of the known environment is no longer the case. So what is happening going forward is really that we need to plan in totally unknown environments, in environments where, you know, you use advanced sensing or machine learning techniques to learn the environment. And as you learn the environment in an online way, you exploit the environment in order to design paths going forward. You could even make the case also for the dynamics part. That's not what I'm going to talk about today here. I'm going to focus more about how do we plan a little bit in unknown environments rather than known environments, which was the case in the past. The fourth and last trend that I see is architectural. So if you come from the control community, which is where I come from originally, you know, the classical way that you would build autonomous machines, like for example, in the case of the DARPA urban challenge vehicles, they would more or less have a hierarchical command and control approach where you would have lower levels of control, where you would do some kind of low level servo feedback control, and then going to higher level trajectory planning, and then going to a higher level, some kind of emission planning, where you're starting getting into software issues such as if you see an obstacle, or if you're too close to the obstacle, do this. If you see another car at a higher speed, do that, and so on. And then, you know, that's essentially the level of autonomy we were able to achieve. But if you're from the machine learning paradigm, then there is a totally disruptive paradigm there, which says, forget the hierarchical and modular command and control architecture. And all I'm going to do is connect the sensors available to the car or to my drone to the actuators. And I'm going to fill in all the intelligence in the middle with some very large neural network. And I'm going to learn the map from sensors to actuators. Okay, so this is the end-to-end paradigm. Who needs models? Why do you care about models? Why do you even care about physics? You can just learn the map from sensors to actuators. So this is something that is a disruptive paradigm. It is not necessarily one that I advocate, but it is something that it is, has some ways to go to compete with this architecture, especially in safety critical architectures. But in non-safety critical architectures, this could be another paradigm. So the question then here for people in my community is, what can we say in this paradigm, and how can we make it a potentially trustworthy and safe, and can we make it also composable with other parts of the system architecture? So these are some trends. Our vision here is that it's not going to take all. We will need elements for safe and robust autonomy. We will need, you know, deep learning for perception, because that is the best technology out there right now, as well as we will need to take perception and get new forms of maps beyond SLAM maps, which can reason semantically about the environment, and then exploit such representations now in a feedback loop while ensuring somehow the safety of the components and the integrated system. Okay, this is essentially our vision, the way we approach this, and these are essentially the directions of my research group, and I'm not going to be able to go through all of these things, but essentially we have a thrust in the group on learning and control, and this, we have also a new conference called L4DC, which we just started, and the next year it's going to be at ETH. We are talking about architectures for safe autonomy, planning in unknown environments, as well as the dual side, which is what can control, what can actually ECE fields, I would say to make machine learning more robust and more trustworthy. Now, the way I'm going to architect the talk, the rest of the talk, is by using this classical feedback architecture. So the way we think about this in the group is that we will have a robot, and this robot, excuse me, could be a drone. In this particular, some experiments, it will actually be a legged robot provided to us by the group of Dan Kodicek. We will have some kind of a deep learning as a perception that looks at the world and it detects objects in the environment. And and then you will get here is some kind of semantic or labels that I see an object at that location and that kind of information. That information is aggregated over time to a mapping layer. And what we produce is some kind of a environmental representation using the output of the deep network. And then this map is what actually goes to the planning and control layer, which needs to take now uncertain maps, which are updated continuously, the dynamics as well as the specification, and then try to solve to find paths or controllers to actually get the robot to do what we would like it to do. And of course, this happens in a real-time closed loop sense. Excuse me. Now, the philosophy that we have wrote here is that, excuse me for a second, is that we believe that in this feedback loop, no component will be perfect. Everybody will be making mistakes. Deep learning will be making mistakes. We have to make it more robust, more safe. But then the mapping layer will be integrating such incorrect, potentially, or uncertain measurements, semantic measurements, and then creating maps, which may also be uncertain. And then the challenge for the planning and control layer is to incorporate this uncertainty into their model and then try to think about how to make decisions in these new forms of uncertainty. So the challenge or the opportunity, if you like, here is that deep learning and autonomy bring new forms of uncertainty that we need to incorporate in the feedback loop. And I think that's what we're going to try to scratch the surface and see how we can do some of this. So what I'm going to do now is use this also as the technical outline of the talk. And I'm going to talk mostly, I think, about how we in control systems, we can make, bring some tools from control optimization and, and other fields to try to make this mapping from images to semantics a little bit more robust or sensitive. And then I'll talk a little bit about the other two, and then I'm going to close the loop. So these are some papers. If you're interested in our work here, these are going to be some papers to take a look at. So as I said earlier, the first thing I'm going to talk about is the so-called fragility of deep networks. I already talked about that deep networks are fragile to adversarial attacks, but they're also, you can take an image and just rotate it, and you can classify things. Measurement noise also, sensor noise also makes deep learning fragile. So if you change the contrast on the image, you may misclassify things. And so how do we think about fragility? So one, the way we will be thinking about fragility here is that we have an image, such as the stop sign. It goes through a feed-forward neural network with L layers. And the architecture of such feed-forward networks is that we have a linear layer followed by a nonlinear activation layer, another linear layer, and then you pass all these pixels through, you do all the computations, and then you get an integer that maps to stop. Now you add the same image with some noise, carefully crafted noise. And then what you end up getting is a very different label, which is speed limit 40. So you don't stop, you continue going, and then you have a safety issue. So this clearly shows that we have a sensitivity problem. Okay, so what this means is that slightly different inputs lead to very different outputs. So we have a sensitivity problem, and the question here is, and I think this is a great opportunity for everybody in the ECE department, especially in the signals and systems side of all fields, because this is understanding sensitivity is absolutely something that people know how to do from, the beginning of the discipline. We had to deal with this in circuits in so many other fields. So I think this is things that I think we have uniquely equipped to have lots of tools to address this sensitivity problem. So the way we'll be dealing with this here, and I'm going to try to skip the math, at least in this talk, happy to talk offline for all the math you like, is that we have an input, which is the image. And then if you really think about this, the input goes through a linear layer, okay, which is linear plus an offset. So this is the linear layer, how the equations look. Then you compose it with a nonlinearity, and then you compose it again with another linear layer, and so on. And then at the end, what you get is some number, okay, or you get some f of x, and then there are hyperplanes at the end that tell you what's the integer. So, and then the nonlinearities typically are the sigmoidal nonlinearities, regular nonlinearities. There's a zoo of engineering now these nonlinearities for different types of tasks. So how do people in the machine learning world, broadly speaking, think about fragility of neural networks? And there are two main paradigms. The first one is to say that we will assume the data is adversarial by a little bit, and we will train to accommodate for these adversarial data. And this is the paradigm of robust and adversarial training, which basically says that given data, we assume that this data is going to be adversarial. So we take some perturbation around this by some delta. And then we ensure not that we classify these data that we don't trust, but we classify in a way that even the perturbed data are classified. And this provides some kind of a defense to adversarial perturbations in some norm. And this is essentially the mathematical way of expressing this adversarial training. The other way, and I'm going to talk with, we are working a lot on this as well, but today I'm going to talk a little bit about our work, which is after you have trained a neural network, how do you certify that it is safe? So here, somebody has already trained a neural network using whatever training methodology, and they give you the neural network as a map, which essentially is the linear layer followed by a nonlinear layer. Somebody gives you an image or a database of images or something, some other signal, and you add some uncertainty around the image. You push it through, and you want to know where this uncertainty lies. Okay, so for example, this could be a sensor to actuation neural network in the end-to-end architectures. And you would like to know whether if this was a robot that you were controlling, whether regardless of what the neural network does, you will stay inside this polytope, ensuring that the neural network, for example, is safe. I don't know what the neural network is doing, but this way I can at least ensure that it will stay within a certain polytope where it's safe. Okay, so I'll speak more about this, but if we have a completely new approach to this problem as well. So now, in the certification paradigm, there are also two main subcategories, which is the first one is that if these are linear plus a radial nonlinearity, the radial nonlinearity is essentially a piecewise linear nonlinearity. So the whole thing is a piecewise linear map. So I can convert it into a mixed integer linear program. And this is one approach that people, and the first paper here is really by Katz et al. From Stanford that started to some extent this paradigm. And here the advantage is that they can compute the input-output relationship of the neural network exactly, but they cannot scale because they are using mixed integer linear program, and it's naturally a not scalable problem. So the other approach then that people are pursuing more in the optimization and machine learning communities, they give up on exactness and they say, well, I'm going to do some approximation of the reachable set. So I'm going to compute it with an ellipsoid, or I'm going to compute it with a linear program. And this leads to some kind of a convex relaxation of these problems. And that allows them to scale more to larger neural networks. But at the same time, they pay a price because this is exact, this is approximate. And here the challenge is the trade-off between accuracy and scalability. Here the problem is squarely scalability. Okay, so our approach is going to be mostly in this category. So now the way we approach this problem goes back to actually a long forgotten connection between neural networks and dynamical systems, or if you like, control systems as well. And that is, I can think of a neural network like this, which is, I have a neural network that has some input, you pass it through a linear layer and then nonlinear and so forth. So I can think of this as a dynamical system as follows. I have the initial state, which is the image. I pass it through a linear layer. And then I go around to the nonlinear layer, which is this, and then I get something, and then I pass it through the linear layer again, but this linearity may be different than that one, making this a time-varying linear system, where the notion of time is actually the layer, the number of layers. So if you equate time with layers, you can basically get that this neural network with L layers is exactly the same as passing this initial condition through this dynamical system for L time steps. Okay, of course, we didn't do anything. We just changed representation. And then you can think about what happens in time 0, intermediate level 1, intermediate level 2, and then you can think of this as a trajectory of this dynamical system. And the reason we want to do this is, as I said earlier, is understanding the sensitivity of this neural network should be somewhat similar to trying to understand the sensitivity of linear time-varying systems with a nonlinear feedback. Something that you would learn in your linear systems course, and maybe with some extensions to nonlinear systems. Okay, so what can we say now about understanding the sensitivity here? Okay, so this is more or less the same. So what can control people say about the sensitivity of such architectures, which is a linear system composed with a nonlinearity? Well, we don't like nonlinearities computationally. We can maybe analyze it, but we would not be scalable. So if we want to do it in a scalable way, what we would do is we would look at the input-output relationship of the activation functions and try to come up with a convex over approximation of the nonlinearity. So if this is a ReLU nonlinearity, for example, we would try to have a convex over approximation of that ReLU nonlinearity. And this is something that we know how to do. It goes back to results actually in the 60s, and then with more recent results on integral quadratic constraints from in the 90s. And this is essentially our approach for this problem at a high level. Okay, and we can do this for any of the known activation functions, whether it's the sigmoid or the ReLU or leaky ReLU or any of those. Okay, this slide just tells you how you go from the ReLU function to this quadratic constraint. Happy to bring that back and discuss it later. So, but this is essentially our key idea of which I present here for a one-layer neural network. We want to analyze properties, robustness, safety, sensitivity properties of the original neural network. And then what we do is, we don't change the linear layers, we keep them the same. We can deal with linearity, even if it's time varying, that's fine. What we do is we change the activation functions with these quadratic over approximations. And then the advantage is, rather than analyzing this, which is a nonlinear problem, this becomes now a semi-definite programming problem. But it is conservative, meaning that properties that hold for this automatically hold for this, but properties, safety properties that do not hold for this may or may not work for that. So what kind of properties can we analyze this way? Well, we can analyze safety as computing the reachable set of a neural network, robustness, local Lipschitz, and I'll talk a little bit about the Lipschitz property, detection confidence, when you pass an image through, how confident are you that you've detected the right thing, closed loop stability if you want to do small gain type analysis and so forth. So just to give you an example, here is how we can use this to compute the Lipschitz constant of a neural network. So this is a Lipschitz constant. You can think of this as a fundamental measure of sensitivity of the neural network. Lipschitz constant means if I change a little bit the input, you know, what's going to be, how far off the output will be. Okay, so if I change the input in some 2 norm, you know, the Lipschitz constant bounds how far off the outputs will be. So the Lipschitz constant is very important for a variety of reasons. First, you know, if we take an image and we perturb it by a little bit, we can immediately get a quick certificate of what's going to happen on the output. But it's also interesting in the sense that it affects generalization bounds in machine learning and so on. We are not working on that currently, but it's been viewed as a very fundamental property for also learnability of neural networks. So even though it's a fundamental property, there are very, very, very few. In fact, our method is mostly the state of the art right now to compute the Lipschitz constant of a neural network. And so essentially, this is what we did. I don't want to go through this. This is more or less what the paper says. And our approach that appeared last December at NeurIPS is both the most accurate, and these are the only other 2 approaches that have some measures of computational approaches for computing the Lipschitz constant, as well as the most scalable in the sense that here we can show experiments, and this is on a laptop, not on some AWS server, where we have, you know, 500 layers with about 100 neurons per layer. So this is a 50,000 neurons neural network. So this is, you know, orders of magnitude below what people in computer vision would use, but it's certainly within the realm of what people in, say, deep reinforcement learning use. So if you use deep reinforcement learning for, say, controlling a robot, and you would like to know how to compute the safety of your neural network controller, then this gives you an approach, and this should be within bounds of that computation. But for vision, we still have work to do. Another thing you could do, and this is actually what we will need for the rest of the talk, is to, if I give, to push distributions through. So we don't just push a set or adversarial noise, but if we have an image which may be corrupted with some noise, and this could be probabilistic Gaussian noise, then you have some ellipsoid, confidence ellipsoid, and you want to push it through, and you may not be able to compute the exact confidence ellipsoid on the output, but you can get an over approximation of the confidence ellipsoid, or you can get a lower bound of the probability that you are in some set. And this allows you to say things such as you pass the image through the neural network, and you can get a lower bound that, you know, the probability that I saw a stop sign is at least 90%. And this is the kind of confidence measure you need, and this is exactly what we will need in the next level at the mapping level, at the mapping layer that's coming up next. So this is a little bit an overview of our approach for verification. I do want to say something about training because I'm personally very excited about this, and that is that even though adversarial noise may corrupt your data, it is carefully crafted noise that does not appear in nature. In nature, what will happen is, you know, you'll get misclassification because it snowed, or because there's rain, or there's environmental reasons why, if you train your neural network on images like this, it will test poorly when your test data is on data that is very far away from the distribution that you trained. And how to deal with robustness of this type of out of distributional but natural rather than adversarial and norm bounded is something that is now emerging as a new challenge. And very excited to, if you're interested in this topic, because we have some very interesting results for all kinds of environmental challenges such as snow, contrast, brightness, fog, and other things. You can look at this paper on arXiv, and actually on GitHub yesterday, we released our code for this if you're interested in this kind of a problem. So this is now, rather than a verification approach, it's actually a training approach of how to train neural networks to increase the detection of the tiger in these conditions, given data here. So how do we have robustness from here to here? That would be a talk in its own right, actually. So I've talked a little bit now about the deep learning network of how to certify that it is safe or get guarantees of confidence. Now I want to switch a little bit to the mapping layer, and these are some papers I will talk about. And here what I'm going to assume is that the deep network that we discussed earlier gives us semantic observations, and we want to build some kind of a map here. So now let's talk a little bit about the mapping world. And if you see the mapping world, as I was saying earlier in the talk, there are two types of maps out there. Historically, people focused a lot on going from point A to point B in a safe way, and that gave rise to these so-called geometric maps, where you go around and you create geometric maps of the world. You figure out where which part of the environment is free, which part of the environment is cluttered, and then that would allow you to find collision-free paths. Now, precisely because we have deep learning that can now detect objects in the environment that was not available 10 years ago, now there's a challenge of not only to create geometric environments, but I would like to know what kind of objects there are in the environment, not just whether there is a free path for me to go there or not. And that leads to this so-called semantic mapping. This is a term that is being coined now, which is maps that deal with the semantics of the environment, what kind of objects there are, what kind of relationships between objects, such as a glass is on top of a table. And we want to reason about the sort of the semantic of the environment. So we will assume now in this approach that we have something, that the deep network is giving us something like a semantic observation. So for now, I'm going to abstract the deep network, and the mapping layer will be getting a frequency, of observations that say, I just saw a chair. I am 80% confident that it's a chair, and I saw it at this location and/or at this bearing. Okay? That's the kind of observations that we will be getting. Now, it may be wrong. It may also miss something. And now, given such observations, I want to create a map, let's say, of all chairs in a building. Okay, and something like that. Of course, what's going to happen is that sometimes you will see one such chair, sometimes you'll see nothing, sometimes you'll see 5 of them. So the number of observations is random at any time. You will also make mistakes. Okay, you may say it's a chair, and maybe you misestimated the probability, or you detected something incorrectly, or whatever. And then the other thing that happens when you deal with this is that you have the problem of data association, which is, well, I just saw a chair and 2 doors. I missed this other chair. Okay, so my deep learning, that's what it was able to give me. But and I want to evolve in an environment. Which of these chairs did this a chair come from? Is it this chair? Is it that chair? Is it this chair, but it just changed because I moved the robot a little bit? So you have a combinatorial problem of mapping sensor observations to mapping mapping objects, and that is a combinatorial problem that essentially is known as associating the data to the map. Okay, as you get new observations, how do you associate it with a map? And this is a problem again that goes back all the way to the radar tracking days. I just heard a ping from an aircraft. Which aircraft did it come from? It's very much the same problem, but this is now at the semantic level. Okay, so what we developed here is a technology known as semantic SLAM, which at an input takes the classical SLAM inputs. Okay, so these are the feature detectors, the IMUs, and all of that. But it also now takes the output of the neural network as an input. So this semantic observation gives us now streams of object detections with the information, the semantic observations I was telling earlier. And then what it gives us as an output is a map, a semantic map, as well as the state of the sensor, which is the state of the robot, which in this case is localization. So it localizes the robot in a semantic map. Okay, so this is essentially what we're doing. So just to give you a little bit of a sense, so we will assume we have access here to the metric input, which is the classical, you know, you would have a IMU, whatever, here you would have the feature detector. This, you know, we also run it in a situation where we actually don't have this input and all we have is vision. We also run it in this configuration as well. And then, you know, for the semantic, we have some kind of a deep neural network that our friends in the GRASP lab, Kostas's group, is giving us, which takes images and tells us, oh, I just saw a car at this location, and this is, we use our techniques to say, this is how confident I am. And then the output, it's best to show it through a video, is that we create semantic maps of the world. So this is what the robot sees. And you see these objects. I see a chair, I see the whiteboard, and then creates a semantic representation of all those objects. And also the green curve here localizes the robot in this semantic world. Okay, so this is where the robot thinks it is in this semantic world. So it uses also the objects to anchor itself in this new semantic world as it gets more and more semantic information from the deep network. Okay, this is essentially a higher level view of what it is. I'll probably skip how we do it. And I'll skip the approach for how we do it. It's interesting in its own right. Happy to discuss after the talk about it. So now, does this work well? Okay, this is a technology that is, the code is is patented almost. It's about to get a patent. We're going to release it soon. If you have any interest in this, please let us know. And then here's how it works. So this is the problem of semantic localization, which is given a map, this is the map of Karlsruhe in Germany, where you know the map. You don't have to build the map. But given a map without any GPS, localize yourself in a city by just detecting objects in the city. Okay, so this is, if you like, you can think of this as vision-based localization, where the deep network is giving us detections. We anchor those detections to the map. We try to figure out what are the most likely semantic anchors here, and then we localize ourselves in a totally unknown environment without any GPS or anything else. So this is the problem of localizing using semantic observations. The dual problem here is the problem of semantic mapping, where you know where you are, maybe not perfectly, but you know where you are, and you make a map of semantic objects. This is not a terribly interesting map of chairs in a building. And chairs we chose chairs because they're vague, and it makes the problem of data association a little bit harder. Which chair did I see? And that makes the combinatorics harder a little bit. Now, this is actually something that we will be using in the ERC with Purdue, where we're going to be using semantic mapping count, for example, the number of fruit of the tree. Okay, so this would be one way of estimating how many objects, how many fruits, or how many oranges are there on this tree. Okay, so this is the kind of technology that we will be using going forward. Okay, and then semantic SLAM does essentially both, and I can skip this slide, which is that it doesn't have a map initially. It builds a map, and as it builds a map, it improves its localization. And then as it improves its localization, it updates the map in a continuous cycle. And this has very good properties also when it comes to things like loop closure and things like that. Okay, so I'll show this later, when you can see when SLAM techniques have a problem with loop closure. Actually, our technique is something that performs much better because you have global anchors to attach yourself to, and then you can use sort of more geometric SLAM to fill in the gaps in between. So this gives us a new type of a map, a new type of a representation. And now the challenge for the control people and the planning people is to bring in such new representations that come from geometric and or semantic maps, and then plan paths in these spaces. So I think the planning and control people tended to avoid bringing complexity into the environmental map. And now what we need to do is embrace that we will have, as we send robots out in the wild, we will have very uncertain representations, and we need to exploit those in the planning process. And I think this is what we will do next, which is looking at, when you look at either geometric SLAM or now semantic SLAM, which has deep network as an input, you get representations that look like this. If you're in the classical SLAM, you get something like occupancy grid maps. There are other mapping technologies as well. And this is just something that tells you which part of the environment is free and which part of the environment is an obstacle and or which part of the environment is unexplored. Okay, but it's essentially a geometric map of what is free and what's not free. In our representations, we get a semantic map, which is also uncertain. It says that our deep network saw something. We've seen some detections here for the last few seconds. And here we are estimating that it's most likely at this position, there is a chair, but it could also be a door, but it could also be a table. We are not 100% sure. So we have discrete uncertainty, but we also have continuous uncertainty in the sense that this could be, somewhere there. Okay, and we could also have other uncertainty like orientation, and one could have even richer semantics like relationships between objects later. So the question now here is, how do we plan in these maps, whether it's an occupancy map or a semantic map? And this is to some extent what we are working on now. So if you go back to the architecture, all of this architecture essentially is now abstracted as a map. Okay, so the deep network and the semantic mapping technology, all of this is abstracted, and whoever is designing this box has to basically say, well, somebody is giving me a map with uncertainty, occupancy grid, semantic mapping, whatever. I have a specification, which could be as simple as go from point A to point B while avoid obstacles, or something more elaborate if you want to have more rearrange the objects in the room, for example. That could be something that you could do if you have semantics. Okay, or take these objects to the kitchen and those objects somewhere else. Those are the kind of new missions now that you can do at higher levels of autonomy. And then given that and the dynamics, you would like to now design paths and controls that actually take to the robot. And this is a very challenging problem to do. We have uncertainty, so we will not get a proof that says, yes, under these conditions, the robot is guaranteed to do this. But we will be able to get algorithms that compute the paths or controls, depending on what level of abstraction you think about this problem, that maximize the probability of satisfying the safety specification. Okay, so, and this leads here usually to some form of an optimal control problem. And I am not gonna spend too much time here of how to solve it, but it is a complex problem in the sense that it has robodynamics here embedded. It has a measurement model as far as what is the robot measuring. We need dynamics of the map, or we can think of the map as being updated frequently in a more elaborate scheme, especially if you're in future. You have a map that says that at the next time, the map, given this sensor, will be updated like this. You have your safety specification, which could be, again, as simple as go from point A to point B, or something more elaborate. And then you may want to also minimize a cost along the way. A very hard stochastic optimal control problem with also discrete things. It's very hard to solve. Yet, if you are in the planning world, we were able to use sampling-based approaches, which can be probabilistically complete in the sense that if a solution to this problem exists, this algorithm will find it with with some probability. Of course, you may have to, unfortunately, wait a while, depending on the complexity of the problem. But, you know, so if you have problems that are extremely constrained, this will be difficult. But if they're loosely constrained, then you should be able to find quickly paths here. The key idea of the sampling-based approaches here is that it doesn't, in traditional robotics, the sampling-based algorithms typically sample the physical sort of locations of the robot. Here, you also have to sample the uncertainty of your map. Okay, so you may want to, you know, sample some directions, not because the robot can get to, but also because you can increase or significantly reduce the uncertainty about the map. And this is sort of some new idea that we are exploring here. So, so here, this is some experiments in collaboration with Vijay Kurmar's group, where the robot is supposed to meet some higher level autonomous plan here. And here there's basically just geometric uncertainty, nothing semantics. It's supposed to go to these places. It doesn't know where the boxes are. Somebody can also change the map by throwing more boxes. And because you can do all of these things fast enough, you don't really, you know, things work out well for these kind of geometric maps. When you go to semantics, and this is a little bit where COVID hit us before we can do experiments with semantic maps. So I only have here some kind of a simulation. I'll have later an experiment with this as well. You know, so here you could have a swarm of 20 robots in a totally unknown building with unknown geometry. They have to do a very complicated mission, which we can express in something known as the temporal logic. And, you know, they're supposed to go and deliver supplies to the green agents, which we don't know who is who. So we have uncertainty about the semantics. And we also don't know where they are. There's some uncertainty about where they are. And also there's an adversarial agent, 9, that we need to avoid. But we don't know whether 9 is here or whether 9 is 8. So we don't know that. But we have sensing, and we have a camera that detects. And based on that, we can complete this mission. And we share the map among the robots. So they don't really communicate. They just have a shared cloud-based map. And then when the mission is completed, they all have to exit from the exit at the exit spot, but they don't know where the exit is either. Okay, so this is kind of the mission that we would like to see executed in hardware over the next year or when COVID allows us to do. And this kind of is a similar type of a mission, which I will skip in the interest of time, with UAVs, with 20 UAVs in an urban environment, more or less. Now, just to start concluding a little bit, here we have tools that if you're interested, you can get. So if you're interested in our work on the making machine learning more robust, there's some code that we have released on GitHub for libstp, and slightly, this is for computing Lipschitz constant. This is about reachability computations. Yesterday, we released on GitHub our robust training paradigm for dealing with things like snow and those kind of things. So that is also there. If you're interested in the semantic slam, this is being close to being patented. We'll release this soon as well. And then here we have VeriSig, which is one way of approaching safety here. And we're working on something called SafePlan, which is based on the ideas I presented. So I was able to tell you so far how each of these components work and how to make each component better, but we still don't know whether the whole thing works in hardware if you put all the components together. And that's going to be the last thing I want to say. And this is something we have been doing the last 8 months with the UAF4SAR project. And that is in collaboration with Kostas Daniilidis. We're more or less the same architecture. We've implemented this in hardware now. So here we have the object detection, which is essentially our neural network, which gets essentially these key points. We also have the semantic mapping. The output of the neural network goes to the semantic mapping, and then these maps now go to our planner. We also have another neural network which estimates human meshes because we want to track humans in the environment. And then this goes to LiDARs and all those things, and that goes to essentially Dan Kotychek's Legged robot. So we wanted to see if we close the loop, ideally I would have some compositional framework to show that all of this works theoretically, but I wanted to see empirically if all of this works given the deep network in the real. And here's the experiment, which is going to actually be presented next week at IRIS. And here the mission is we have the robot from the essentially Ghost Robotics. And here you can see what the robot sees. And here is the semantic representation of the world. It's trying to track the human and avoid all other obstacles. Everything is completely unknown. Okay, so it has the deep network that detects the objects. It creates the semantic map, and then it uses the planner to achieve this mission using the semantic map as the input to the planner. And of course, it worked fine. And then we felt confident to just change the environment, completely different environment, without changing anything of the code. It's a measure of robustness. And also, you don't know, maybe the deep learning is going to feel that this is a different surface. Maybe the controllers will feel, but everything worked fine. We didn't have to retrain anything, which is a major problem. When you have a machine learning approach, you change the environment, you have to retrain basically all the machine learning things. Here, because everything was robust, every component was designed with robustness in mind. They composed well, and they worked in a variety of environments in a very robust way, achieving more or less the same mission. Again, unknown geometry, unknown objects. All you have here is your sensing capability and deep networks, your controllers all working together. And then we decided to go even up. Then the real test is to really go outside. And we took it outside. This is sort of our new robotics facility. And, so again, going outside is a bigger challenge. Some of the lighting changes that could affect the deep learning detectors. But all of that worked, again, very robustly. And now that we are able to achieve simple missions, semantic missions using the deep learning detectors, now that gives us confidence to go at higher levels of autonomy. So with that, I'll stop and tell you what is next. And I think there's lots of opportunity on the interface between machine learning, optimization, control, signal processing. I think one challenge is to go towards dynamic environments from static environments. And then the other thing that we're working on is how to explore notions of risk in planning when we plan in unknown environments. Many more things, but I'm out of time, so I'll stop here and take any questions. And thank you again for the invitation.
So thank you, George, for a fantastic talk. This was a lot of information here. I'm just fascinated by the whole thing. At this point, I want to open the floor for questions. Please turn on your camera and state your name so we have some person and name association when folks ask questions. I can just let me get started. When you're using these sensor-based techniques for SLAM, I guess it's my favorite question is aren't you worried about sensor drift? How do you take sensor drift into account when doing these training algorithms?
Yeah, to some extent, yeah. So if you have something like SLAM, you would be getting drift, and that would lead to things like closure or things like that. To some extent, the way I think about this is that what we are doing provides some less frequent but more global, especially when you're dealing with localization, more global anchors to the drift problem. So for example, you could close your eyes and open your eyes, and then you would see, oh, I detected a Starbucks. And that anchors you, and that helps you with the drift problem because you reduce that error, and then you may drift again, and then you may see another semantic anchor. And that helps you ground in a sort of in a drift. So drift will happen and will affect the feature detectors and the geometric side clearly. But when you fuse it with the semantic detections, especially if those semantic detections have good, relatively good localization of the object as well as and/or its pose, if you do, we also do pose, then I think that helps with the drift. It doesn't eliminate it, but it helps. You have one.
Do you reset your anytime you find a known landmark or a position?
The whole map gets updated. The whole map gets updated.
You reset it.
Everything gets updated. Yes.
When the robot was walking towards the end in the first floor corridor along, it seemed to be slipping a little bit, or maybe it was just my video. But those kind of slip conditions are typically very difficult to track, even whether it is, because you think you have stopped as you're looking, and actually the legs are slipping. So there is no real sensor to measure whether you've reached a zero velocity point.
Yes, it could be. I would have to ask my colleague Dan Kodicek about what technology they use at the legs for the slipping. Could be.
I think we have Professor Saurabh Bakshi has a question. Saurabh?
Yeah, can you hear me?
Yeah.
Yeah, so I really enjoyed the presentation. You mentioned guarantees and verification in the same breath as deep models, which is not very often heard.
Yeah.
So I was wondering, in the first part of the presentation, when you're talking about improving the verification of models, if you could bring in some semantic information like you did in the second part of the talk. For example, could you use knowledge about how a video will change on the physical space due to some known information about the physical space or the speed of the vehicle? If I got it right in the first part, you were not using that.
You are absolutely correct. I mean, I can get back there, whatever it is, but you are absolutely correct. And my new motto is models improve robustness. That's exactly my new spin here. And this is exactly what you're saying. And this is the slide I'd like to say. So the way we approach this problem here in training robustness, you could also do it for the verification side, is if you have a model of how this image is transformed to this image, you can either have it because of physics, or you can learn it using whatever method you want. If you have such a model, then this model is precisely the one that's causing the data perturbations. And this is precisely what you need to train your deep network to be robust against. And this is exactly what we're doing. So we need some kind of a model. Now you can do this also for a signal. If you have a signal and that signal is perturbed, if you have a model of that perturbation, you should exploit that in training your deep neural network to be robust against that model of perturbations. And we have not, so this is exactly what we are doing. So we want to know how much can snow, if we had a model of snow, or if we had a model of contrast, or if we had a model, there are some models that are very easy to obtain, like rotations, of course, these are geometry. And then you can train neural networks to be robust with respect to, for example, rotations. People have already done that, but they have not done it in other things which are harder to model. And, but I agree, if you have a model of how images, the input of your input may change, you should exploit that either in the robust training, which is what we do, or in the certification side. Absolutely true. The certification side is essentially mathematically the certification problem. The training side is the overall max-min problem. So you can exploit such, so rather than here having that the data is perturbed by some delta in an additive way, there is a model that perturbs this data point. And then you're doing that max-min with respect to that model. That's more or less what we do. That's our new approach. And you can do it either for the max-min or you can do it for the inner product, which would be the certification. We have not done the certification, we have done the outer.
Got it. Thank you.
Any other questions for George?
Yes. So, hi, Josh. So my name is Humphrey, and I'm a PhD student in the ECE department. It's a very interesting presentation, and I just have a question about the combined robustness of the system. So even though each component in the system is designed with robustness in mind, but how do you guarantee that combined feedback system is robust? Because we know from the famous John Doerr paper that even though each component in a system has good robustness margin, the combined system wouldn't guarantee that robustness margin.
It's a very good question. We do have a paper, which I don't know if I cited it here. We do have a paper that is not compositional. What your approach you mentioned is compositional, that I have robustness here, robustness there, and I have some way of composing and so on. We have two papers now where we analyze a neural network with a control system in a feedback interconnection as one big system. Because, let's say, loosely speaking, the neural network, you can think of it, if you like, as a piecewise linear system, if you've already trained it. The control system is a linear system. You put them in feedback interconnection, you should be able to do either an MILP approach or some convex approximation approach, an optimization approach for the overall system. But the approach is not compositional. The approach does not say, I analyze the neural network, I analyze the control system, which is what you're proposing. I think that would be an interesting problem. I agree completely. Right now, we have looked at the composition, but in a non-compositional way, which of course creates its own scalability problems. But I agree with you, it's a very interesting problem. It's a great time, in fact, to be a PhD student, I would say, because these are very exciting problems. So, yeah, so.
Thanks.
Okay. So if there are no more questions, we would officially like to finish the seminar at this moment. I think the Icon Center, Saurabh, Shreyas, you want to take over?
Yeah, sure. I think so. That's great. So we're gonna have an
Thanks,
opportunity.
George. I stay here, correct?
Yes.
Yeah, I was saying we'll take a 10-minute break, right?
Okay.
So essentially, people can use the restroom, etc., and then we'll start up again around 11:20 or so. And this is for students or postdocs or anybody actually is welcome to come back. We just have a free-flowing discussion.
Excellent. Yeah.
Okay,
And
so
then we will have another call, another at 12 o'clock, or we will meet for like a lunch, e-lunch, just the faculty, George, the Icon faculty, and maybe anybody else and the professors who are interested. So maybe we talk more about the university side of things more than
Okay, sounds good.
So yeah, 11:20. Folks come back.
All right, thank you.
Thanks.